finish up main memory, talking about some main memory scheduling policies. Actually tackling the problem one of you brought up last time, which was if you actually prioritize row over hits, don't you run into a problem when you have multiple threads or applications sharing the main memory. So we'll tackle that issue, and hopefully we'll get to virtual memory. But your homework 6 is out. Actually, it was out yesterday, I think, right? It's due April 16th. But I would strongly recommend that you actually solve it before the exam. So you could kill 2 birds with 1 stone, right? You would do the homework and you would prepare for the exam. Because all of these topics, will very likely be on the exam. Okay. Lab assignment 5. You guys are done? No? Almost? Hopefully everybody will get extra credit. So if everybody actually optimizes their design to be very, very fast, you can get extra credit. I guess that could work the other way around too, right? Nobody optimizes their design and everybody's design is within 1% of each other's. I'll tell you, run into prisoner's dilemma. What if somebody optimized their design? Alright, so optimize your design, I think, so that you don't run into that dilemma. Midterm 2, you know this, and hopefully you'll be prepared for it. Hopefully everyone will ace it. Here you cannot run into prisoner's dilemma, probably. I guess you could. Okay. So last lecture we talked about a lot of things. We covered the DRAM subsystem in great detail. Hopefully you know all of these things by now. We covered refresh and DRAM controller. We talked about power management basics. This was kind of an aside in lecture. But as I said, everything we talked about in lecture is related to computer architecture. So you should know these also. We talked about Bloom filters. I will briefly spend a little bit of time on this. Because I didn't give you the full picture, I think. Alana talked to me after class, and she told me that Bloom filters are much more than what I explained, and I agree with that. Basically, what a Bloom filter is, it's a compact and approximate way of representing set membership. Okay. You have some elements. You want to represent whether or not those elements are in the set. Right? You have an address. You want to know whether or not that address is present in the set. So one thing you could do is basically have 1 bit for each address. Right? 1 bit per address to say present or absent. Right? The problem is you can have many rows in DRAM memory, for example, many addresses. Right? So this is not approximate, right? This is exact. This tells you whether or not the address is present or absent. So present means 1, absent means 0. That address is not there. The Bloom filter essentially shrinks this bit array, if you will, to a smaller size and makes it approximate, meaning an address is present if the bit corresponding to that address is set. But this is not necessarily correct because now you have fewer bits than the number of addresses, which means that this 1 may actually be representing some other address that happens to map to that bit. Okay. This is called a false positive. Because you have fewer bits than the number of addresses that can potentially be in the set, you can have aliasing in those bits, in that multiple addresses can map to that bit. And if one of those addresses is present, then you deem all of those addresses that map to that bit as present, even though they're not. Okay? So that's why it's an approximate data structure. So you don't have the false negative, because if an address is present, you definitely set the bit that corresponds to that address. So if your problem is such that you can tolerate false positives but cannot tolerate false negatives, this is a good data structure. You should be able to tolerate false positives. And the problem we talked about, representing whether you should refresh a row or not, it's okay to, this Bloom filter says, you should refresh the row if the bit is set. Okay. It's okay to refresh the row, even if it doesn't need refresh for that interval. Right? That's why false positives are tolerable for that problem. Whereas false negatives are not tolerable for that problem. Right? The row, you don't want to zero when you actually really want to refresh the row. Remember that I'm talking about the context previously. So of course, you would still like to minimize these false positives, right? Which means that now you have a question of how do you index into this bit array. Right? One thing you could do is actually take a bunch of bits from your address, the same bits here. Let's say your Bloom filter has 1024 bits. Then you take 10 bits from your address to figure out which bit that address maps to, which presence bit that address maps to. Now what does this mean? All of the addresses that have the same 10 bits map to the same location. Okay. What if which means that you get aliasing among those addresses. You may not be utilizing these 1024 presence bits very well. So what is usually done in a Bloom filter is you go through a hash function to determine which bit an address maps to. Okay? Aliasing means two addresses map to the same bit. Two different addresses. Yeah, collision. Yeah, aliasing or collision. That's right. These are used collision or aliasing. These are used in similar ways. Okay? So that's the idea. This allows a very easy way of testing set membership. Right? Is this address a member of the set? So I'll let you read this. This is from actually one of my students' papers, Vivek's paper, that talks about how a Bloom filter operates. I'll leave this to you. But this was a data structure that was proposed in the 1970s, mainly for this purpose, and it allows very easy implementation hardware. You can think of a bit array and the hash function, right? Okay. Now you can think of the key issue is if you cannot tolerate a lot of false positives, what do you need to do? You can make the bit array bigger, right? So that the probability of two addresses colliding in the same bit reduces. Or you can design a better hash function. Again, you'd like to reduce the probability of two addresses colliding at the same bit. Or one other thing that's used is represent existence or set membership by setting multiple bits. Okay? Instead of saying, I set only one bit, and if that bit is set, then this address is present, you have multiple hash functions. Hash function 1, hash function 2. When you get an address, you check both bits that are specified by the hash function, and if both bits are there, then you declare that that address is present. Now what does this do? Now, you need to test for multiple bits, which means that the likelihood of two addresses colliding in those exact same bits reduces. Right? They may collide in one bit, but they may not collide in the other bit. Which means that hopefully your false positive rate reduces as you add more hash functions. Of course, as you add more hash functions, your hardware complexity also increases. Right? Yes?
So what's the difference between this and hashing?
So it's essentially like a hash table, very efficient hash table. Right? The main difference is a hash table, when people talk about hash tables, it's not approximate, it's not probabilistic. Right? Whereas here, you have probabilistic data structure. So what happens in a hash table, you get a collision, so you rehash, and you look up another location. Right? So that's the main difference. But if you have a probabilistic hash table, this is essentially an implementation of a probabilistic hash table. Okay? Yes?
Is it possible to study during the manufacturing manufacture of a certain memory, can we study the environmental conditions that lead to variation in this capacitor charging time?
So,
if we could study that and come up with a certain pattern, then we could overcome the need for this kind of prediction.
I didn't quite understand that, but that's very difficult to do. It's very difficult to figure out. So basically, you're saying eliminate the variation somehow, right?
No,
or
what I mean to say is understand the variation, so that you know that this part will most probably be a good capacitor. This
Oh.
will be a
Okay.
also good capacitor.
So
Understand the factors that contribute towards it, and then because
so that's very difficult to do. That's very difficult to do. And it turns out the variation is relatively random in the array. It's very difficult to control. If you could control it, yes, you could do that. Right? If you could say, oh, this part of the array has this much retention time, this part of the array has this much retention time, this part of the array has this much retention time, but it just doesn't work out that way. The manufacturing process is not that nice, if you will. At least as far as we understand today. Okay. Okay, so I'd encourage you to read, actually, both papers. So Vivek explained Bloom filters nicely, and he also talks about the hardware implementation. And I'll let you read it, but you can imagine how it's implemented. Okay, any questions on Bloom filters? So you know what they are now. Excellent. Let's briefly review what we covered last time. This is going to be very brief. I'll just show you pictures of it. You remember the DRAM organization. You remember, hopefully we've covered the address mapping, right? Where does a physical address get mapped to in the DRAM system? And we talked about this being influenced by virtual addresses, virtual to physical mapping that's determined by the operating system. And we will talk about this more today. That's why I'm flashing this. At the end of the lecture, we'll talk about how this translation is done, virtual page number to physical frame number translation is done, and how that affects, obviously, because of this translation, the operating system has some control over which column, which bank, and which row an address gets mapped to. Right? And we will see that the operating system has a very similar control over which location in the cache an address gets mapped to because of the virtual to physical translation. So remember that. We talked about the DRAM controller quite a bit. There are many functions of it. We talked about its main function, if you will, ensure correct operation. But it has other functions, buffering and scheduling requests. And we will talk a lot more about this today. Okay. This we covered. What are some of the scheduling policies that you can employ in the DRAM controller? First come, first serve, oldest request first. Simple. But you could do better than this, which is implemented in many controllers today, which is first ready, first come, first serve. The idea is to prioritize the row hit request first. You have a buffer. The memory controller has a request buffer. And the request buffer contains all the requests. Let's say we're controlling, we have per bank request buffer. We covered that also. Per bank versus across all banks request buffer. So this request buffer contains requests to row A, B, A, C, D. Let's say this is the oldest one. The idea, and then bank 0 has row B open, let's say. Because the last request happened to be to row B, and it was serviced. The idea of row hit first scheduling is to prioritize the accesses that go to the open row first, because they take much shorter. And assuming, so these are priority levels, if you will. Among all of the first priority level is row hit first. If nothing is row hit, then you look at the second priority level. If there are multiple row hit requests, then you still look at the second priority level. Second priority level, prioritize requests based on age. The goal is to maximize row buffer hit rates, maximize DRAM throughput, and minimize request latency, if you will. We talked about that, but I will not. Okay, we talked about the row buffer management policies also, open versus closed row, and adaptive policies. You should know about that. So for the rest of this lecture, I'll assume an open row policy, where the DRAM controller keeps the row that was last accessed open to be able to exploit row buffer locality. But there's a trade-off there too, as we talked about. Okay, I'll skip this after flashing. So remember this request scheduling policy. The goal was this, right? And as one of you brought up last time, this is a good policy for a multi-core system. No. That's right, exactly. If one processor always keeps accessing the same row, then another processor will never get a chance to access that bank, right? And that's the problem. And I think I have shown you this before. Is that correct? Do you guys remember this? Yes. Those of you who weren't sleeping remember. So this was the problem. We have a streaming application and you have a random access application. And assuming your row contains consecutive addresses, a streaming application means you have a stride of 1. Right now you have all these terminology sets, which means that you're accessing consecutive hash blocks or consecutive words in memory. And if you have a first ready, first come, first serve scheduling policy, I'll call it row hit first scheduling policy, what the memory controller does is it prioritizes accesses from the streaming application for a long time until the streaming application stops accessing this row. Right. Then the other application gets a chance to access, assuming it's had older requests. But there could be another problem over there, right? If you do oldest first scheduling, you're implicitly prioritizing an application that has many requests, right? That keeps sending requests. Because it looks like there are more requests, and the requests look like they're older, because they come before a less intensive application's requests. So there's fairness in both aspects. There are fairness issues in both aspects. Row hit first as well as oldest first. So okay, let's look at this. So you could actually write this really easily, right? You can do this if you're interested. You can do this in existing systems. People, although Intel and AMD may have changed their controllers, so this doesn't happen very often anymore. But you could do this in 2007, 2006. You could write an application like this, which essentially copies one array to the other. I'll call this stream. And it's a streaming application because it has sequential memory access. Basically, every access is a cache miss, and you go through 2 arrays in sequential order. As a result, you get very high row buffer locality. So simulations show that you get 96% or 97% hit rate in the row. And it's very memory intensive. Every access is a cache miss. So this is the controlled experiment that we had done to actually exercise this.
How do you make sure that we access the cache?
Well, if you know the cache size, line size, block size of your cache, you ensure that you have a data structure that's big enough, and you touch the first byte of the data structure. Right? That's exactly actually how you ensure it. Assuming your line size is in bytes. Okay. So you could also write the same application, except it does random access. Right? Copy one array to the other. You determine the indices randomly. And it turns out this has 3% hit rate in the row buffer. As a result, it's random memory access, and similarly memory intensive. So when you put these together, what happens? Well, I've kind of shown you, but I'll animate it also. Let's assume the blue application is streaming, the other application is random. Let's assume streaming application opens row 0 in the row buffer, and this is the request buffer, and hopefully you're familiar with this. So streaming application accesses row 0. In the meantime, requests arrive in the memory request buffer, and the scheduler from the memory request buffer prioritizes streaming application because it keeps sitting in the row buffer, right? And this is what happens. I could go on forever now. That's right. So at that point, then you can start servicing. So that depends on the memory request buffer size. That's a very good point. That also depends on how many requests this application can send, right? Remember, we covered the core, how many requests it can generate. If the number of requests that can be buffered in the memory scheduler is smaller than the number of requests that can be generated by this core, then this fairness problem will not happen. But usually that request buffer is larger because you have many cores sharing that request buffer. So as a result, you can make a calculation with a row size of 8 kilobytes and a cache block size of this big, 64 bytes. You can have 128 requests of the streaming application service before the random application. Okay? And if you had done these studies in 2006, you would get results like this on a 2-core system. This is on Intel Pentium D. At that time, it was Pentium D. This is the slowdown of the application compared to when it's run alone on the same 2-core system. So Stream slows down by about 18%, whereas the random access application slows down by about 3x. So that's the unfairness. Actually, you can do the control experiment. Runs 2 streams together, you see that they slow down by an equal amount. Or you could put 2 random applications together, you see that they slow down by an equal amount also. You have to do that control experiment, right? Make sure that you don't have some other effect. Okay, so this happens with other applications also. If you run this hog, if you will, we call this a memory performance hog, it affects the performance of other applications. ECC, and this is the Microsoft virtual machine. I don't know if it exists anymore. You guys, it does exist? Virtual PC? No? Okay. Okay, so this problem becomes bigger as you add more cores onto the system. So this is another example. It's a simulation example where you run 4 different applications. LibQuantum is actually a quantum computing simulator, and this is a network simulator, and this is the H.264 video decoder. And I think this is a genome sequencing application. Let's assume that you're running them together on a cloud computing system. This application slows down by 5%. This application slows down by 8x compared to when it's run alone. So you get very unfair slowdown of different threads. And it turns out that this LibQuantum looks very similar to the stream that I just showed you. It keeps streaming through memory. It has very good row preferred rate. It has very high memory access intensity. So why is this bad? Let's say you don't care about fairness. Well, of course, we probably should, perhaps, right? Depending on maybe this is an interactive application that you care about, right? This also leads to low system performance because it turns out these cores that are slowed down, they're not making that much progress, right? They're just waiting for their memory request to be serviced. So your system utilization goes down. Your cores do not make progress. You're vulnerable to denial of service. Someone can actually write this application easily. You can get priority inversion. So regardless of, so you can go in the operating system and change the priority of this application to high, right? Make all of these nice, and nothing will change. Assuming these are the 4 applications that you're running in the system, because you have 4 cores. And operating system will schedule all of them onto these cores. So basically, you're unable to enforce priorities, if you will, at the operating system level. And you get poor performance predictability. What happens is, now the performance of an application really depends on what else it is running with. So here, for example, Omnet slows down by about 4x instead of 8x. And this happens in many different systems. You can test these. So why does this happen? Well, because it happens because these different threads, if you will, threads of execution or cores, interfere with each other in DRAM in this case. And we didn't handle that interference well. Right? The memory controllers, pins, and memory banks are shared. And when you have a shared resource, you have a scheduling decision between these different threads. Whereas what the controller did was, the controller didn't care about the threads, right? It only cared about the row buffer, what row was open here, and what was the age of the requests. As a result, it didn't really handle the interference between the threads well. Now, why is this a big problem? Because if you look at DRAM, we've already talked about this, but DRAM is off-chip, right? You have DRAM, and you have memory controller on chip. And you have cores here. You can easily put more cores on this chip. But you cannot easily add more controllers. Why? Because controllers require more pins going into the DRAM. So this interference becomes a bigger problem as we go into the future because your bandwidth per core, memory bandwidth per core is reducing. So let's take a look at this interference a little bit. Why does this happen? It happens because of resource contention, right? You have these resources, banks, buses, row buffer, and you can get conflicts in those resources. That's why you need to schedule wisely. And I will show you also these different threads can also destroy each other's parallelism in memory banks. This will become more clear. If the thread is running alone, it could utilize all of the banks concurrently, right, if it has multiple requests outstanding. And all of those latencies will overlap. So the thread essentially stalls, waits for only one of those requests, if you will, because you're overlapping the latency in the different banks. But if you don't handle this interference well, if you have multiple threads, even though that thread has multiple requests to different banks, other requests can get delayed in the banks, right? Which means that all of those requests can be served serially instead of in parallel. And we will see that this is a problem. Okay. So I think this is the same thing that I showed you. So the problem happens because the controllers are unaware of this inter-thread interference, and they simply aim to maximize DRAM throughput. So this is an important thing you should take away. The controller tries to maximize how much data is transferred per second, if you will, or per time unit from DRAM. But this is not the right thing to do in this case, right? You may want to reduce the amount of data throughput you get, but enable some cores to make more proportional progress, if you will. Because if you maximize the data throughput here, you may be prioritizing only one core that utilizes that data throughput really, really well. Right? That was what happened with the stream. You can have only one stream here and a bunch of different randoms, and that stream will be the only thing that the system is executing at that point in time, if you will. Executing meaning making progress on, making forward progress on. Make sense? So that's the problem. The row hit first policy unfairly prioritize threads with higher buffer locality. So how do you fix this problem? I'll give you some solutions to this that we've been looking into. Basically, you need to design this memory controller to be aware of, I'll be very fuzzy here, quality of service, if you will. Which means that when it's resolving contention between these different cores, when it's scheduling requests, it needs to consider high system performance, high fairness to applications, instead of just throughput that is obtained from this data list. And I'll add to this, it needs to be configurable by the system software also. Why? Because of the reason I stated before, right? If you have a high priority application, if the memory controller doesn't know that that application is high priority, how is it going to prioritize that? So before this was not a problem, right? In a single core system, you did not need to tell the memory controller, oh, I'm running a high priority application. That's the only application you're running. Whereas right now, you have many cores. Maybe we should be able to tell the memory controller that this application, this core, is a lot more important than the other one. Because I'm running, I don't know, what's your favorite application? I'm running my favorite game on it. While at the same time, the virus checker kicks in, right? You don't want your favorite game. You don't want to mess up your gaming experience because of a stupid virus checker, right? So these are some of the issues that we should think about going into the multi-core system. We'll cover multi-core more, but this is a perfect place to cover it. That's why I'm covering it right now. Okay, so basically these are the things that we want from the memory scheduler. How do we get that? Basically, you need to be aware, the memory controller needs to be aware of these threads. And I say threads because it's really not the cores, right? A core can have multiple threads also. Remember fine-grained multi-threading? A core can have multiple threads. In fact, in many systems today, cores have multiple threads. And within a core, one thread can be more important than the other. Make sense? So how do we actually solve the problem? I'll give you some ideas that we've explored. The first idea is stall time fair memory scheduling. basically, if you go back here, there was a problem with the slowdowns, right? The slowdown of different threads are extremely different. So why don't we try to equalize these slowdowns? So that we can make all of the threads make proportional progress compared to when they run along. So that's the main idea in this stall time pair memory scheduler. Somehow, the controller tries to make the threads sharing main memory experience similar slowdowns compared to when they run along. So this is the idea of pair scheduling. This could also be good for system performance because now you're allowing threads to make progress, right? Proportional progress, if you will. So the idea is to add some logic into the memory scheduler to estimate each thread's slowdown compared to when it's run alone, and schedule the requests in a way to balance those slowdowns. So how can you do this? I'm not going to go into too much detail, but you can define a DRAM system to be fair if it equalizes slowdown of equal priority threads. And the memory controller can keep track of two things. One is the DRAM-related stall time when the thread runs with other threads. And one is the other is ST alone, the stall time when the thread runs alone. And it can compute the slowdown, stall time shared, stall time alone, which is a relative increase in stall time. Stall time means the core is waiting for the memory request, right? It's stalling, if you will. It's not making progress. And the idea is, for each thread, when you compute this memory slowdown, try to balance those. Simple, right? So how can you do this? Well, every cycle, you figure out you have a slowdown value for each thread. If it happens that one thread's slowdown value shoots up because you've done the wrong thing, prioritize that thread. Right? Okay? Basically, for each thread, the DRAM controller tracks the stall time shared. Remember, the stall time the thread has when it's sharing the resources with other threads, when it's sharing the memory controller with other threads, and estimates stall time alone. Now, here's an issue, right? Maybe you're going to ask that. How do you estimate that? Okay. Well, I'll give you the basic idea. I'm not going to go into too much detail, but, well, I guess I don't have it here. You can think of stall time shared. So you have some alone stall time when you're running alone, and you're adding more stall time because there's some interference that happens, right? Additional time, I'll call it. Additional time due to interference. So if you can estimate how much a thread is delayed because you preferred another thread's requests over this thread's requests, then you can figure out this alone. And the memory controller has that information, right? It can add more counters to figure that out. Memory controller knows when you have multiple threads, memory controller needs to figure out which request is to be scheduled next. And if thread 0's request is scheduled when there is thread 1's request also waiting for that bank, you know that you delayed thread 1 by the amount of time it takes to service this request. Okay. So you can simply add a counter for each thread that we call this the T excess, if you will, stall time excess. The excess stall time that is introduced because the memory controller preferred some other thread's request over this thread's request. And you can simply, and stall time shared is easy, right? Because you can compute this by looking at how much time the core is waiting for memory. And that's easy. And you can compute this in the memory controller, and you can simply figure out stall time alone by subtracting the stall time excess from stall time share. Okay? Now it becomes complex when you consider main memory, but you can read the paper if you would like to look at how complex it is. Yes?
Okay, so you're assuming that if you have a memory request outstanding, then you might not be part of it.
So, yes, let's assume that for now. But you don't need to assume that. You can actually figure out this information at the core level. Core. Right? Stall time share. The core can say, if there's a memory request at the head of the reorder buffer, if you will, then it's stalled. Okay? Yes?
Could we also have a priority inversion in this case? unless we have a certain inheritance of priority between low, medium, and high priority tasks, you could still have inversion.
So, yeah, for now, assume that every task is equal priority. You can actually configure this, but I will not go into that. Okay? I'm assuming every task is equal priority. Otherwise, it doesn't make sense to equalize the slowdown, right? If a task is high priority, you should really speed that up at the expense of other tasks. Okay? So every cycle, the DRAM controller computes the slowdown by dividing stall time shared over stall time alone, and also computes unfairness, which is the maximum slowdown in the system divided by the minimum slowdown. For each thread, you have this slowdown value. Slowdown value for each thread I, and the maximum of that is the maximum slowdown in the system. Minimum of that is the minimum slowdown in the system. And also, so this is the unfairness in the system, if you will. If it's really high, then you're prioritizing one thread over the other quite a bit. If it's close to 1, then everybody is slowed down fair. And then, controller checks if unfairness is less than a bound, if you will, and this could be system software configurable. It uses basically row hit first, because it's not being unfair, right? Now you can optimize the DRAM throughput. But if it's unfair, if unfairness is not tolerable, then the first priority level it used in its scheduling policy is to prioritize the thread that has the maximum slowdown. The goal is to reduce this unfairness. Does that make sense? The second priority level is still row hit first. The third priority level is oldest first. Okay? So let's take a look at how this works. But these are the same threads. Thread 0 stream, thread 1 random. And these are some of the counters that you need, not all of them, of course. You have the unfairness and you have the alpha value. Let's say maximum tolerable unfairness is 1.05. And ideal is 1, right? 1 means, what is unfairness? I'll write it here so that you guys can remember this. That's the maximum slowdown in the system divided by minimum slowdown. Well, in this case, we have 2 threads, so it's easy to compute the max and min. So, let's say thread 0. Thread 0's request is serviced. Let's say slowdowns are initially 1. At this point, thread 0's request is preferred by the memory controller over thread 1's request because the memory controller is row hit first. Now what happens is thread 1's slowdown increases, right? Because thread 1 is delayed for a while. Which means that unfairness increases. But unfairness is still tolerable. At some point later, again, thread 0's request is preferred. Now thread 1's slowdown increases a little bit more, and unfairness becomes intolerable. Which means that in the next scheduling decision, the controller picks the request from thread 1 instead of thread 0, even though thread 0 has a row hit here. Because unfairness was too much. Make sense? Now, thread 1's request is being serviced. This increases thread 0's slowdown, right? Because now thread 0 is being delayed. Because you've serviced thread 1 while thread 0's request was outstanding. Which means that your unfairness goes down, right? So now your unfairness becomes 1.03 in this example, which is less than alpha. So the next thing you service is from thread 0 because you're doing oldest first scheduling now. There's no row buffer hit. Right? Which increases the slowdown of kind of both threads. It increases the slowdown of T1 because you prefer T0's request over T1. But it also increases the slowdown of T0 because this would have been a row hit, right? If that application was running alone. So you keep track of that also. That's what makes this a little bit complicated. But still unfairness is within check. And then at some point later, again, unfairness becomes intolerable. You go back to the fairness-oriented scheduling policy, which prioritizes T1, which slows down T0 again, and unfairness becomes tolerable again. So you keep switching back and forth between the fairness-oriented policy and the DRAM throughput-oriented policy to keep this unfairness in check. Does that make sense?
It's sort of like the corporate predictor
it's different, right? Tournament predictor, what it does is, for a given branch, it selects which predictor to use. Whereas here, you're trying to, it's a scheduling problem, basically. You need to pick which request to select next.
Here you're choosing the scheduling algorithm.
I see, in that sense. Yeah, in that sense, there is some similarity, that's right. But it's a very loose similarity. Right? You're choosing a scheduling algorithm based on a dynamic condition. In that sense, it's similar. You're choosing a branch predictor based on a dynamic condition also. But I think that's the extent of similarity. Yes?
You have like a hard-coded number of registers that keep track of programming everything because you know exactly how to get that.
That's right, exactly. You need to have enough registers as the number of hardware contexts. So these are not software threads. These are hardware contexts that are sharing the memory control. And it's much more than this because you need to be able to estimate stall time, shared store time. Okay. So this is one skip. Yes, you have.
I just had a question. So this doesn't have a lot of overhead.
You can read the paper. But this does have overhead. This is a little bit complex to implement, but this was our first proposal to fix the memory scheduling problem that's present in multi-core processors. So we have better proposals right now. So it's in a sense, it's a good way of thinking about how to design a fair system. You can think about applying this principle to other things also, right? For example, if you have a disk controller, you have a similar problem, right? So you have requests from different processors, if you will, or processes. Then how do you design a fair scheduler? In fact, the problem is even worse in disks, perhaps, because random access latency is a lot worse than the streaming latency. And you may want to design something like this over there too. Estimate the slowdown somehow and try to balance them. Make sense? The problem exists also in caches, which we will see later on. If you have a shared cache between different cores, again, which process do you give more cache to or less cache to? Okay. So, okay. I'll tell you about another problem due to interference, which I promised earlier. You've seen by now that processors, cores are designed to tolerate latency of memory requests. Out-of-order execution, in particular, makes use of non-blocking caches to generate multiple requests in parallel. And servicing these multiple requests leads to overlapping of latency. We'll talk about random execution when we get to prefetching, but this is another way of overlapping latency. You generate multiple requests at the same time. This notion is memory level parallelism. We talked about this when we talked about MSA charts, how to implement non-blocking caches. Now this works only if those requests actually go to different banks, right? If those requests that you generate go to the same bank, then you cannot service those requests in parallel. You cannot overlap part of the latency. Let's assume that they go to the same banks. And only if the DRAM controller actually services the multiple requests in parallel in DRAM banks. Let's say the assumption is multiple requests go to different banks for now. In a single core system, this is true, right? Assuming that multiple requests generated by the same core go to different banks, the controller will service them in parallel. That's the purpose of banking, right? That's the purpose of interleaving. But when multiple threads share the DRAM controller, and if your controller is not aware that a thread is generating multiple requests to different banks, it can service each thread's request serially and not in parallel. So let's take an example. Let's say you have a single-threaded machine, a single core. You have two banks in the memory system, and this thread does some computation, and it gets two load misses next to each other, sends them to the memory controller, and these are the misses. One of them goes to bank 0, row 1, the other goes to bank 1, row 1. Let's assume the row numbers are inconsequential. The point is they go to different banks. And the controller starts servicing one in one bank, And in the meantime, the core stalls because it's such a long latency, and you have only so much reorder buffer and reservation stations. Assume that this is 500 cycles, and you have, I don't know, a 64-entry reorder buffer. Okay, and the controller services the other, in the next cycle, next DRAM cycle, it sends the other request to the other bank. And the core stalls while these two requests to different banks are outstanding. When the first request is done, the controller sends it back. When the second request is done, the controller also sends it back. And the core continues when both requests are complete, assuming that you need both of the results to do some computation. Right? So this is what happened here is by servicing the two requests in parallel in different banks, you overlap the latency of those two requests. The core stalled approximately for one bank access latency instead of two. Okay.
Can you ever make them exactly overlap?
Can you ever make them exactly overlap? Yes, you can, right? If you can generate both requests at the same time, and you have multiple channels, and both requests go to both channels, and you can return the responses at the same time, you can make them exactly overlap. Okay. Yes, that requires more. Okay, so what happens if you put two of these threads together? Let's say thread A and thread B. They both do the same thing, for the sake of the example. They both generate two DRAM requests at the same time, and these requests get sent to the memory controller in this order. And the memory controller, let's say it takes thread A's request to bank 0 first, start servicing it. In the next cycle, it takes thread B's request to bank 1 and starts servicing it. Both threads stall while their requests are pending. And then the bank 0 finishes servicing this request. The controller takes thread B's request to bank 0 and starts servicing it. And then this other request finishes, and the controller takes thread A's request to bank 1 and starts servicing it. And all of the requests complete after some point. And then the cores now can continue computation. Now what happened here is, even though you could have serviced A's request in parallel in different banks, this did not happen. The controller serialized those requests. Serviced this request after the other. Which means that each thread now stalls for approximately 2 bank access latencies. Okay. Now this is bad, right? The controller could have done something smarter. Is that true? Yes, it could have handled. That's right, exactly. So the controller was not aware of threads. That's why it handled these requests in the order they were generated. Whereas it could have been smarter, it could have been parallelism aware, as we called it, parallelism aware and thread aware. When it received these requests, let's say it picked one thread A's request to bank 0, it could have realized that thread A has another request to bank 1, which could be serviced in parallel. And instead of picking thread B's request, it could have picked thread A's request to bank 1. And if it does that, this is what happens. Thread A's requests get serviced in parallel. After some point, one request completes. The controller picks thread B's request to that bank. And after some point, the other request gets complete, and the controller picks thread B's requests. But in the meantime, this core can now make progress, right? Because both of its requests got serviced, and it could start computation. This core still cannot make progress because its requests have been outstanding. But compared to this picture, it's okay, because it still gets its request complete at a similar time. Whereas what you gained is, this thread is significantly accelerated. So you saved quite a bit of cycles here. Why? Because you preserved the parallelism of each thread's requests in the banks. So average stall time, if you will, is approximately 1 bank access latency here, and approximately 2 bank access latency here. So if you average those, you get 1 to 1.5, which is better than 2 here. Does that make sense? So that's the idea. So how do you actually implement this? So this actually becomes a bigger problem if you have more threads. And even if you have more banks, you cannot have, because of this issue that we talked about, you cannot have many banks, which means that it becomes more important to preserve each thread parallelism. And it also becomes more important when you increase the out-of-orderness of the cores. Because one of the major benefits of out-of-order execution is actually the tolerance to this memory latency. And if you cannot tolerate memory latency anymore, you've implemented out-of-order execution in the cores, but you're wasting all that logic that you implemented to find independent instructions. Right. Okay? So how do you actually implement this? Yes? This slide.
Over here, what if thread A had multiple accesses over here? So how would you draw the line that, let's say thread A had 50 accesses?
Yes.
So that would throw B off.
Yes, we'll get to it. We'll get to it. That's a very good question, though. So if thread A had many accesses, then you've got to be careful as to, you don't want to prioritize that, right? Because it's, even if it has very good parallelism, because it has bank confidence. But we'll solve that problem soon. Yes?
You could have another factor like alpha, which you had earlier for reference, and use that for threads. That probably qualifies.
That's a good thought. We'll solve it in a different way. But you could introduce something else, which we will introduce, to actually make sure that threads that have lots of requests do not hog the memory. Okay? So how do we implement this? Let's assume that all threads have similar amount of requests for now. How do we implement this? Basically, we want to be parallelism aware, meaning that we want to preserve the bank parallelism of each thread. So how do you do that? You'd like to schedule requests from a thread to different banks back to back. Right? If a thread has requests to different banks, you would like to send them back to back. This preserves each thread's bank parallelism. Now, of course, this can cause starvation, partly because of the reason that you talked about. Right? If a thread has many requests, one after another, other threads don't get served. So, the second principle, you can batch the requests to ensure that starvation doesn't happen. And the idea here is the controller groups a fixed number of oldest requests from each thread into a batch and prioritizes that batch over all other requests. This is a principle that's used to ensure forward progress. In fact, this was first proposed to be used in disk controllers a long time ago in the 1960s, late 1960s. If you have many requests, service them in batches. Finish the first batch, and then move on to the next batch, and then move on to the next batch. That's the same idea here. We'd like to group a fixed number of oldest requests from each thread into a batch, and service that batch before all other requests, and form a new batch when the current one is done. And within the batch, you can do this. Within the batch, you can schedule requests from each thread back to back. This way, you don't have starvation. If a thread is very aggressive, it's not going to hog all of the resources because only the batch requests get prioritized over others. So let's take a look at how this works. Pictorially, you have two banks again. And let's say we have requests from these 4 different threads. The controller first forms a batch. And batch forms naturally because the latency to access this bank is very high, whereas there are lots of threads generating requests, so you have a backup, if you will, in this scheduling queue. So what does the controller do within this batch? Well, it prioritizes, let's say, thread 0's requests first and services them. In the meantime, some other requests arrive, but they don't get batched. Because that's the purpose of batch, right? If you put them into the batch, then you're prone to starvation. Then, let's say the controller prioritizes T1's requests. Now T1's requests get serviced. T1 can make progress. Then the controller prioritizes T2's requests within the batch, but not those. Okay? Then the controller prioritizes T3's requests within the batch, and then moves on to form a new batch. That's the idea. You could again use this principle for many different controllers. We've used it for memory controllers, and this is the distinguishing factor in a memory controller, the fact that you have many different parallel things that's happening. Many different parallel banks. So okay, the idea, you exploit parallelism, bank-level parallelism within a thread and overlap latency by scheduling requests back to back from that thread. This causes starvation. You eliminate that starvation by batching requests and prioritizing the oldest batch. Now let's go through the implementation very quickly. How do you do batching? This is very simple. Each memory request has a mark bit associated with it. And when the controller is ready to form a batch, which means that there are no requests in the previous batch, it basically goes and looks at its queue and marks up to a number of requests, oldest request per bank for each thread. And these marked requests constitute the batch. And these requests are always prioritized over unmarked ones. And we figured out why this is good, right? Because you never reorder a younger batch over an older batch. Okay? Now the key question is, how do you actually prioritize requests within a batch? You could actually use any DRAM scheduling policy within that batch, right? You could do row hit first to exploit row buffer locality. But we also want to preserve bank parallelism. If you did this, then you won't preserve bank parallelism, right? We've already seen this. So we would like to service each thread's request back to back. So how do you do that? The key idea is the scheduler computes a ranking of threads. So it basically says, this is my ranking. I have 4 threads sharing the memory controller. I form a ranking of the threads. Thread 1 is prioritized over thread 2, is prioritized over thread 3, is prioritized over thread 4. And higher ranked threads are prioritized over lower ranked ones. Why is this good? Because this improves the likelihood. Now you're servicing a thread request back to back, right? Yes?
So when you say that to preserve intra-thread bank parallelism, you want to service each thread request back to back.
Exactly.
But that's assuming that the thread has made requests to
different banks. Yes, that's right.
The thread is down about
Yes, that's right. If the thread has not done it, you cannot do it, and we will try to fix that problem also. So the key question again is, how do you form this ranking? Exactly because of the problem you state. If all threads had made requests to all banks at equal amounts, then this is simple, right? Forming the ranking is simple. You can just form any ranking, right, across the threads, because all threads are equal, if you will. But it turns out not all threads. Some threads have 1 request to 1 bank. Some threads have 10 requests to all banks. And some threads might have imbalance between the banks, right, depending on what kind of bank conflicts they get. So ranking scheme actually affects system throughput and fairness because of that. Our goal is, again, always maximize system throughput and minimize unfairness, right? Equalize the slowdown of threads. So what does maximize system throughput mean? You would really like to minimize the average hold time of the threads within that batch. Does that make sense? Remember, let's go back here. Oh, that's a long animation now. You could reverse engineer the memory controller. So how do you maximize throughput? You minimize the average hold time, right? You'd like to minimize this red across all threads. Okay. Well, it's a faster animation. How do you minimize unfairness? Basically, you would like to service the threads that have inherently low stall time early in the batch. Now what does this mean? A thread that is making few requests, they inherently have low stall time. Right? So you'd like to prioritize those threads. The insight is that if you delay a memory non-intensive thread that is making few requests, that results in high slowdown for that thread. Whereas if a thread is making 1,000 requests, if you delay it a little bit, it's not going to slow down that much anyway. Does that make sense? So that's the key insight. So it turns out that if you would like to maximize system throughput and minimize unfairness within the batch, if you do shortest stall time first or shortest job first ranking, you achieve kind of both. And we will see with an example. And this is a very well-known principle, right? Shortest job first. That maximizes system throughput. So how do you do that? Basically, you have the controller estimate each thread's stall time within the batch and rank the threads with shorter stall time higher. Does that make sense? So if a thread has very few requests, a short stall time, rank it higher. Now the stall time also takes into account parallelism, as we will see. Yes?
Should it be priority be coming from a higher level, like the lowest level?
So, okay, here we're assuming again all of the threads have equal priority. We can configure this controller later on.
Secondly, shouldn't we be concerned with what kind of application this processor will be designed for? Because if it's a general purpose application, then maximizing system throughput is fine. But if you're trying to make a real-time processor,
Yes.
dedicated for tasks, this may not be the best way to go.
That's right, yeah. If you're designing a real-time processor, then it's a very different system. You want to, like hard real-time, if you want to provide hard real-time guarantees, then you may not even want to be sharing the memory controller between different threads. So this is more for, that's a very good point. This is more for general purpose processors. The goal is not to provide hard real-time guarantees. Okay? Okay. So how do you actually achieve this ranking? Basically, this is the idea, shortest call time for ranking, first rank. How does the controller figure this out? It computes two values. One is the maximum number of mark requests to any bank. I'll call this max bank load. And this is the number of requests that a thread has to any bank in memory. It ranks the threads with lower max bank load higher. Does that make sense? If a thread has a smaller number of requests, maximum requests to any bank, it means that its stall time is low. And we would like to make that thread go fast. Otherwise, it'll slow down too much. The second is total number of mark requests, and this is used to break ties. A thread is ranked lower if it has too many requests across the entire memory system. So let's take a look at how this works. Now it's a more complicated example, right? In the paper, you can see actually an even more complicated example with row buffer hits and misses. And this is a paper actually you should probably read. Let's make that assigned reading, since we're covering it in detail. We have 4 banks, and we have 4 threads, thread 0, thread 1, thread 2, thread 3. Let's take a look at these values for each thread. Let's take thread 0. So I'm going to remove all of the requests from other threads. If you look at thread 0, the maximum number of requests it has to any bank is 1. And it has total 3 requests, so its total load is 3. Now let's take a look at thread 1. The maximum number of requests it has to any bank is 2. And its total load is 4. Now why is this max bank load important? Because it really determines the stall time of the thread, right? The thread is backed up in this bank. Which means that if it's executing alone, this is the stall time. Its stall time would be 2 bank access latencies. I'm ignoring all other bus latency here. Okay, for thread 2, again, the maximum number of requests it has to any bank is to either bank 1 or bank 2, which is both 2, but it has a total number of 6 requests. And thread 3 is the most intensive thread, if you will, in terms of memory. It has 1, 2, 3, 4, 5 requests to bank 3, which determines its max bank load. And its total load, total number of requests is 9. So the ranking we would form would be to rank thread 0 higher than thread 1, because thread 0 has the minimum max bank load, minimum maximum number of requests to any bank. And then thread 1, and then thread 2 is ranked lower than thread 1 because it is more memory intensive, if you will. And then thread 3. Thread 3 is ranked the lowest because it has the highest stall time, if you will, alone. So let's see how this actually improves performance, at least within this batch. So this, let's say this is your baseline scheduling order, which is the same as arrival order. Let's say this is the time in which requests are serviced. So at time unit 1, we're servicing these requests in parallel in these different banks. At time unit 2, we're servicing these requests in parallel. At time unit 3, we're servicing these requests in parallel. Let's compute the stall times of different threads. If you compute the stall time of thread 0, if you look at when is this thread's last request serviced, well, after time 4, right? When is T1's last request serviced? Again, after time 4. When is T2's last request serviced? After time 5. When is T3's last request serviced? After time 7. And average stall time is, well, if you compute the average, it's 5, assuming I didn't do a calculation error. Now, what happens with parallelism over batch scheduling? Remember, we computed the ranking. T0 ranked higher than T1, ranked higher than T2, ranked higher than T3. And all of these requests are already in the request bucket. Well, first, all of the banks service T0's requests, because the controller says T0 is the highest ranked thread. Prioritize that. Which means that you finish all of T0's requests after time unit 1. And all of its requests are serviced in parallel. Then, the priority order says prioritize T1's requests. Which means that, well, in time unit 1, there was no request from T0 to bank 0, but there was a request from T1 to bank 0, which means that bank 0 can service T1. Okay. And T1's requests are finished after time unit 2. Then the prioritization order is thread 2, and thread 2's last request is finished after time unit 4, and T3's last request is finished after time unit 7. So in a sense, this is much more regular. What you've done is we preserved the parallelism of the threads, and we ranked them in shortest stall time first order, which led to an average of 3.5 bank access latencies within the batch. So you improved average stall time by 30% by preserving parallelism and ranking threads in shortest job first order, if you will. Make sense? So that's the benefit of having a memory controller that's aware of threads, as well as aware of how intensive the thread is, as well as how much parallelism the thread has. Okay? So what's the resulting scheduling policy to implement this? Basically, marked requests are prioritized over other first. This is the notion of batching to prevent starvation. And within a batch, the priority order is like this. Actually, the priority order could be switched here without losing any performance. You prioritize row hit requests, but you don't need to do that. You can actually prioritize the higher ranked thread first, and then row hit request next, and then the oldest request next. So this, you still exploit robo for locality, and you also exploit inter-thread bank parallelism, but there's always a tension between these two, and I'll let you think about that tension. So this is worth conserving, which means that it's a priority order, right? If you have an unmarked request to a bank that doesn't have marked requests, you don't want to not service that request. You don't want to waste bandwidth, memory bandwidth, if you will. And marking cap is important. You can think about this and read in the paper also. Basically, if you put too few requests into the batch, then that's not good, because you can destroy robo for locality, right? Because you prioritize threads based on that. If you put too many requests in a batch, now you can cause starvation, right? Let's say if your batch has 100 requests in it, and a request from a memory non-intensive thread arrives while you're servicing this batch, it'll have to wait all of those other requests first. So it's important to determine these things. Okay, you can read the paper for more. Okay, so to wrap up, I guess, this discussion, what is the benefit of all of this? These are results, simulation results from 4-core, 8-core, and 16-core systems with a bunch of workloads. You can read the paper for more. And this is unfairness in the system. And remember, unfairness, it's maximum slowdown in the system divided by minimum slowdown in the system of any thread. And there are 5 bars. This is row hit first scheduling policy. This is first come, first serve. It doesn't take into account row hit requests. Ignore this one. This is a fair queuing approach that's employed in network routers, if you will. The next one is full time fair memory scheduler. And the next one is parallelism over batch scheduler that I described. Both of them. So if you look at first 30, first come, first serve, the row hit first scheduling policy, it becomes very unfair. And this is unfairness in terms of max divided by minimum memory slowdown average across many workloads. So its average unfairness is 5, if you will. So there's a 5x disparity between the slowdown of the thread that has been slowed down the most and that has been slowed down the least. And if you use these thread-aware mechanisms, if you do just oldest first scheduling, it's a little bit better, which means that row hit first is contributing to unfairness quite a bit, but oldest first is not good enough, right? And you know why? Because if a thread has many requests, its requests will be likely prioritized by the controller because they appear older to the controller. Right? Oldest first is not a fair scheduling policy. Does that make sense? Okay. Whereas if you use these thread-aware memory schedulers, you get unfairness to a relatively low value, especially in 4-core systems and 8-core systems. Of course, unfairness becomes increasing as you increase the number of threads because you have a memory bandwidth problem. And the best unfairness you can get is 1, right? Everything can be slowed down equal. So this also improves system performance if you use these thread-aware mechanisms. This is the system performance normalized to row hit first scheduling policy. In fact, row hit first scheduling policy starts reducing performance compared to oldest first because of the unfairness issues it causes. Again, row hit first scheduling policy is great. It improves performance if you have single core. Maybe I should have shown single core here also. If you look at single core, row hit first, well, I guess in this case it improves performance. Okay, maybe I didn't explain well. But here, the row hit first scheduling policy reduced performance compared to oldest first. But if you look at single core, it's consistently better than oldest first. But because it delays some cores a lot more, in a multi-core system, you can lose performance. So if you look at the 4-core system, the thread-aware memory schedulers improve performance by about 30% in this case, and by similar amounts in other systems. Okay? Any questions? Okay.
In the 8-core, what is the format FRC doing better than FCX?
That's because of what I just described. Basically, it may be that you have an application that has high row buffer locality, and that gets prioritized, and all other cores wait for it. It just turns out that it happened that way in the 8-core because of the workload selection. Because these workloads that you run are different, right? Okay. So let's cover some other ways of fixing this interference problem. We looked at when you have multiple threads sharing the memory controller, how do you schedule requests in a thread-aware manner to minimize interference, maximize fairness, maximize performance? But there are other ways of doing this, which I'm not going into too much detail about, but you should know the basic principles. This is actually allowing us work. And the idea is one other way of reducing interference between threads in the system is to exploit the existence of multiple channels. You have memory channel 0, memory channel 1. You have many different cores. And if you could identify which cores interact nicely with each other, which applications running on the cores interact nicely with each other, and which don't, you can map those badly interfering applications to separate channels. Right? Does that make sense? That way, they don't interfere with each other at all because they're at separate channels. That's the key idea here. So let's say you have 2 channels and 2 cores, which is not going to happen in the future, but this is just to motivate the problem. If you map the data of both of the cores to all of the channels, this is what you could get, right? What happens is this core 1 gets delayed for 4 time units. Stall time is 4 here. Whereas core 0 stall time is 5. But if you map the data of these different applications to different channels, this is what you would get. Core 1 now can make fast progress. Its stall time reduces to 1. And core 0 can also make fast progress because it doesn't get interfered by core 1. Its stall time reduces to 4. Make sense? Basically, the key principles are, this was a low-intensity application. It didn't access memory that much. And this was a high-intensity application. If you separate the data of those, then you can enable this low-intensity application to make fast progress. A similar situation exists with low and high row buffer locality applications. If you have a high application that has high row buffer locality, again, because of the row hit first scheduling policy employed in the memory controller, that application starves the other application that has lower buffer locality. So why don't we put them on different channels? That's the idea. And it turns out this is effective in reducing interference of threads as well. And you could employ this together with some of the memory scheduling policies. That's right, exactly. Okay, so there's another way. So I'm giving you ways of handling interference. One is request scheduling. One is data mapping, if you will. You map the data such that interference doesn't happen, or in this case, channel partitioning. We partition the data to different channels such that interference is reduced. And the third principle is essentially what I call source throttling, or third mechanism to eliminate interference or reduce interference. And the idea here is figure out if a thread is causing a lot of slowdown to some other thread and throttle back that thread. It's a simple idea. Right? If a thread, let's say the streaming application in the previous example, if we figured out that it was causing too much slowdown to some other thread, we could tell its core that is executing stream application, stop sending requests from this thread for a while. Now you can enable other threads that have been slowed down to use the memory system. And that's the basic idea. Of course, there are a lot of details in how you would implement it, and you can read this particular paper to figure out how it's done in one way. The advantage is it's easy to implement. It's actually, there's no need to change the scheduling algorithm. There's no need to change the mapping dynamically. And it can be a general way of handling shared resource contention. Actually, all of these are general ways of handling shared resource contention. And you can think of advantages and disadvantages of each. The disadvantage is, well, you need to figure out which thread is causing trouble to which other thread, right? And you may need to do that in a pairwise manner. Because let's say you figured out the thread that has been slowed down the most in some way, in a manner that I described over here. Let's say you figured that out. You also need to figure out which thread is causing that problem, right? And if you have, let's say, 32 threads sharing the memory controller, well, now you need to keep track of which thread has caused interference to which other one, the most interference. Because if you throttle the thread that has not caused interference to the thread that has been slowed down a lot, what did you do? You will not gain anything, but you will lose performance. Because that thread was not the culprit. Yes?
With this source something like that, always want to only consider one core, because it could possibly be that two, three cores are interacting
That's right.
in such a manner that the slowdown.
Exactly, yeah, that's right. Absolutely right. And you can read the paper. You throttle more threads if that happens. But you're right, it's not only one thread, and that's another potential disadvantage of this. You can lose system throughput by throttling too much. Yes, and that's this. Your thresholds can become difficult to optimize because you need to determine which thread to throttle and by how much to throttle. Right? By how long are you going to stop this thread from injecting requests into the memory system? And I'll let you think about that. And it turns out this is a real problem. It's difficult to implement. Okay. I'll give you one more thing, just to let you think about. What if you had a parallel application? What if you had, so all of these things that I described, assume that the applications were independent, right? They were not cooperating. But what if you divided your application into threads, and they were cooperating? And what does this mean? Remember the picture I drew? You have a sequential portion of your program, and then you launch a bunch of threads that compute things in parallel, and they synchronize in a barrier. Now these threads, thread 0, thread 1, thread 2, blah, blah, thread, let's say 15, are cooperating with each other, right? they're trying to solve the same problem. But they're also, if they're run on a 16-core machine, interfering with each other in the memory system. So which of these threads should the memory system prioritize? Let's go back to memory scheduling again. When the memory scheduler sees 16 of these threads, requests from these 16 of these threads, which of them should it prioritize to maximize the performance of this overall program? That's the issue of handling interference in parallel or multi-threaded applications. Threads are interdependent on each other. And where does that interdependence come from? In this case here, it comes from this barrier, right? The program cannot proceed until all threads arrive at this barrier. Right? Or interdependence can come from locks also, right? If a thread holds the lock, and if another thread is trying to access that shared data, now the second thread needs to wait. So some threads can be on the critical path of execution due to synchronization, and some threads are not. So this is one synchronization mechanism. Locks are another synchronization mechanism. Locks are used to protect shared data. Barriers are used to determine when you can continue execution after parallelism. They both synchronize the threads. And because of this, now some threads can be on the critical path. So if you look at this barrier, you cannot make progress in the program until the slowest thread arrives at the barrier, right? So maybe if you can determine what thread is slowest, you can prioritize that in the memory scheduler, right?
Why don't you just want to make slowdowns in or like that?
So you could do that assuming they are all doing the equal work. But what if, remember the example that I gave a couple of months ago, or last month? We were doing the histogram of the, we were trying to get the histogram of occurrence of each letter in a book. Okay? And we had divided the book into, I don't know, pages. The computation done in each thread for that problem is different, right? Because the occurrence of each letter in the pages assigned to each thread is going to be likely different. Make sense? So, if you try to equalize the slowdowns, which could work in some problems, it may not work in this problem because this thread has a lot of work to do. Okay? So, this is the key question. Now we schedule requests of these interdependent threads to maximize multi-thread application performance. And the idea is, I will not give you more detail than this, but to estimate limiter threads that are likely to be on the critical path and prioritize their requests. And kind of ensure proportional progress, if you will, among the other remaining threads, non-limiter threads. So there are some threads that are limiter. In this case, it's this thread 15, right? It happens to have too much work to do. So you prioritize it. Well, it's not as easy because when you prioritize it, it may become the non-limiter now. Right? You can make so fast progress that somebody else becomes the limiter. So these are some of the challenges in how to optimize the memory scheduler for this kind of applications. Yes?
How can the memory system know how long it will take?
Excellent question. Yes, read the paper. So there needs to be some support. For this particular case, there needs to be some support coming from the compiler or the programmer, telling that this is the amount of work that's assigned to this thread. Yes, and otherwise, the memory system has no semantic information about how much work there is. The situation is a little bit easier with locks. So with locks, you can keep track of what locks are contended. So if a thread is holding a lock that is contended, that other threads are waiting for, you know that you've reduced the parallelism in the program. So you can prioritize the thread that's holding the lock. If the lock is not contending, if nobody's waiting for it, you may not want to prioritize that thread. because there is no serialization problem. Okay, so that's the idea. Hardware and software cooperatively estimate the limiter threads. Thread that's executing the most contended critical section or block, or holding the most contended block, or the thread that's falling behind the most in a parallel for loop. This is a parallel loop, right? Or some areas of synchronized programming. Okay? Okay. So let's wrap this up, I guess. So this interference actually happens not only in the memory controller, and we will probably take a look at shared caches if we have time. It happens everywhere in the memory system, my multi-core system, right? In any shared resource. It could happen in this shared cache. It could happen in the interconnect. It happens here in the shared bus. It happens in all of the shared resources. So the problem today is threads share the memory system, but memory system doesn't distinguish between these threads because of all of these that we've seen before. So we need to design the system such that you have the memory system that's aware of the threads. So that's how you solve the problem. So you need to essentially design an interference-aware memory system that's aware in each of these resources of the different threads. And that employs appropriate policies to minimize that interference. Okay? Otherwise, you're prone to starvation, basically. You can have a multi-core system that you cannot use very well. Okay. Any questions on this? Otherwise, shall we start with virtual memory? Okay. You guys are waiting for virtual memory. I should know all of this, or most of it. Okay, we probably won't finish all of it. I guess we're jumping from one exciting topic to another exciting topic. This is a very relatively new problem. This didn't exist before, right? Before we had a single core, one chip. It did exist if you had multiple chips, right? This is chip 1, this is chip 2, and you could share some memory. I guess I like writing on top of what I write before. But you could share a memory controller across these different chips. But this was a much less scalable system in the past. Meaning, how many of you had laptops that contained multiple processors like this? Probably not many of you, or 0 of you. So how many of you currently could have this kind of system? Probably still. Oh, you have it? You have multiple chips? Yeah, no, not multiple chips. You still don't have this. You still have a single chip, but a single chip has many cores. Right. Exactly. So the problem is a lot more important because all systems are multi-core today. And there's a lot more resource sharing that's happening today. Okay. So now we can jump to a much older topic that's been around for a much longer time. And that's the idea of virtual memory. I don't know how I will cover this, but this will give you an idea. At least when you go back to lecture notes. So these are your readings. I think lecture notes are probably good readings, but you can look at section 5.4 in Patterson and Hennessy. So what do we want? Remember the ideal memory. We should always start for the ideal. And we tried to get some of that. Zero access time, we wanted that, right? That's why we built memory hierarchies and zero cost. And infinite density. One thing we also want is infinite capacity. Unfortunately, that's hard to get. But that's one of the reasons why we built the memory hierarchy. You know, this memory hierarchy, which has a lot of capacity at the bottom here in the disk. But in physical memory, it doesn't have that much capacity. Your physical memory is of limited size because of cost issues, right? You can increase the size, but then you run into cost problems. And another thing we wanted is the zero cost. So all of these are at odds with each other, just to remind you. But we would like to get the illusion of infinite capacity at least. What if you need more of the physical memory that doesn't exist when you're programming? What do? Should the programmer be concerned about how much physical memory there is in the system? Right. Should they, when they're programming, should they try to fit the data blocks into that physical memory? Let's say you have physical memory that's 1 gigabytes, but the data that you're using is greater than 1 gigabytes. Should the programmer manage that? Well, in the old days, the answer was yes. The programmer should do that. And what the programmer did was what is called overlay programming, which, did any of you have to do that? If you had to do that, it's a very cumbersome thing to do. Basically, you need to lay out your data in physical memory, and if you need more data than your physical memory, you need to figure out what to replace and figure out what code blocks should go where exactly in physical memory, what data blocks. And you should do this for the code too, actually. That makes it even more complicated. What if your program doesn't fit in physical memory? Okay. The programmer needs to manage that. Think about that. Yes?
To an extent, this is not on a database system. It's like if you want to store records, you typically do it in such a way that you're just using the buffers that are available.
Yes. So this is still done in some systems. For example, especially, well, maybe some is not the right word. Maybe most embedded systems don't have virtual memory today, and they expect the programmer or the system software designer needs to do something like this. But it's a very cumbersome thing to do. Well, should the programmer manage data movement from disk to physical memory? And the answer that we will give is hopefully no. Right? We've talked about programmer versus microarchitect in all of this course. And if there is one example that has been extremely successful so far in general purpose processing in making programmers' life easier, it is virtual memory. In fact, this could be a very good job interview question. If you get the question, what is the biggest benefit of virtual memory? The answer should immediately be programmers' life easy. Okay? Well, there is another thing, actually, that leads to a problem, which is ISA can have an address space that's much greater than your physical memory size. Right? And it should, actually. Otherwise, you would be tying your ISA to a particular implementation. Right? For example, you can have a 64-bit address space with byte addressability. So how do you manage the mapping of this address space to the physical address space? What if you do not have enough physical mapping? But this is the more important problem, if you will. So the idea of virtual memory is to give the programmer the illusion of a large address space. Let's assume large address space is infinite, so that he or she doesn't worry about running out of memory. The programmer can assume they have an infinite amount of memory, physical memory, but really it's the amount specified by the address space of a program. So you could still run out of that address space. So you may have gotten virtual memory exhausted errors when you write big programs. And hardware and software cooperatively provide the illusion that the programmer has infinite amount of memory, even though physical memory is not infinite. And this illusion is maintained for each independent process. That's the idea. So how do you actually do this? The basic mechanism is simple. It's indirection, basically. So what does that mean? The address generated by each instruction is not a real address. It's not a physical address. It doesn't mean anything from the perspective of all those structures that we just talked about. It doesn't mean anything for this bank, right? That address is what's called a virtual address. It's called the linear address in x86. And there's an address translation mechanism that maps this address to a physical address. This is called the real address in x86. And this address translation mechanism is implemented hardware and software together. And that's a very important part of virtual memory. It's a hardware-software cooperative mechanism. You could do it purely in software, which means that it'll be extremely slow. You could do it purely in hardware, which means that your operating system cannot manage some things, and things may become very difficult. But it's done together. So how does this work? Essentially, you have virtual addresses generated by the program, and you have a virtual address space based on that. Right? That's specified by your ISA. So if you look at your main memory, as your program sees it, you have a virtual address space. And this virtual address space is divided into what is called pages. It's called this virtual page 0, virtual page 1, virtual page 2. And your physical memory is much smaller. I guess let's say 2 here. I did a good job of scaling this. But it's divided into physical frames. Physical frame 0, physical frame 1. And the size of the physical frame is the same size as the virtual page. And there is a mapping between the virtual page number to the physical frame number. And that mapping is maintained by the virtual memory management or memory management unit. A virtual page is mapped to a physical frame, but obviously you don't have enough physical frames to map all virtual pages to. If a virtual page is not in physical memory, then that mapping says, too bad, it's not in physical memory. Right? So you need to manage this somehow. Which means that if you're trying to access a virtual page, well, 3 is in physical memory, virtual page 4, let's say. If the program accesses virtual page 4, there's an address translation mechanism that's consulted that translates this virtual address, virtual page number. I'll call this the address translation for now. We'll look at how it's implemented soon. To a physical frame number. But if the page doesn't exist in the physical frame number, in the physical memory, then it needs to be brought into physical memory, right? So how do you do that? Basically, the virtual memory system brings the page into a physical frame and adjusts this mapping. So obviously, you need to maintain a mapping table here, and all of this needs to be managed, and this is called demand paging. You've probably seen this before, right? Of course, there are issues. Now, what page do you replace? What frame do you replace from the physical memory? We'll get back to that. So where are these mappings stored? These mappings are stored in what is called a page table. Right? The page table is a structure that is indexed using the virtual page number and address, and that gives you an entry, page table entry, that contains the mapping, the physical frame number. And we'll see how that's done. So if you have physical memory only, basically your CPU, your instruction generates a physical address. Whereas if you have virtual memory, now you have this indirection. When you execute an instruction, execute a load or store, you get a virtual address. You look up the page number of that virtual address in this page table, which gives you the frame number, and then you can access memory using that frame number. Right? And the address translation is the process through which you actually translate this virtual address to physical address. Let's cover the case where the object is not in memory. So if this page is not in physical memory, you get a page fault. So once you get the page fault, the page table entry indicates virtual page is not in memory. So how do you figure that out? Basically, for each page table entry, we should look at what is in a page table entry. Actually, let me draw the page table here. So you get a virtual address, some number of bits in the address tell you the virtual page number, right? And using that, you index this page table. And the page table entry contains a bit saying whether the entry is valid or not. If this entry is valid, then this physical frame number is the physical frame where this virtual page resides. And essentially, the physical address is physical frame number plus this thing that you had in your virtual address, which is the page offset. Right? This tells you which bytes in page. And those bits are used, those bits do not change during translation process. Right? Because your virtual page is the same size as your physical frame. Okay, so what if this bit is 0? Meaning that your virtual page that you're looking up in the translation mechanism doesn't exist in physical memory. Then this physical frame number is meaningless. Right? Well, but you have something else potentially stored here that tells you where in disk this virtual page can be found. Or a pointer to a location that tells you where in disk this could be found. Okay? So, which means that if translation gets a page fault, then there's an exception, and that exception needs to be handled. You stop the process, and we know about precise exceptions, right? With precise exceptions, the hardware saves the state of that process and jumps to an exception handler that would move the data from the disk to memory. Basically, the operating system figures out which page, which frame to deallocate from main memory, physical memory, and where to put the new frame, the contents of the new page into, and then adjust the mapping. Okay? You know all of this probably. Yes? Hopefully. It's all refreshing your memory. So, how do you actually service a page fault? This is just to show you the overall system diagram. When the processor gets a page fault, it goes through this page fault handler, and it signals the controller saying that read this page starting at address X and store starting at disk address X and store it into memory address Y, this physical frame in main memory. And this is done by having multiple controllers involved, if you will. You need to go through the I/O controller to access the disk, and disk usually uses the direct memory access mechanism through which it sets up a transfer from the disk into memory of all of that page. And after some point, this I/O controller signals completion, saying that, oh, I've done the transfer of the page from the disk to main memory. Processor, now you can continue with the process. So it interrupts the processor, and the operating system resumes the process that was suspended. So the whole system gets involved in page fault handling. Okay. The page, yes?
Where the page table stored?
Yeah, we'll get to it. We'll get to all of that. It has to be stored somewhere, right? But let's look at what it is for. A page table is also per process. Each process is its own virtual address space, so that a programmer can get the full address space for each program, right? And this also simplifies memory allocation, sharing, linking, and loading. And I'll let you think about some of these, but I'll show you the sharing here. Let's say if there are two processes, and they share a page in an OS or library, for example. What you can simply do is map the virtual page 2 of this process to that shared physical page, and virtual page 1 of this process to that shared physical page. That's how you can share pages between different processes. That's how you can share OS code across different things. You can have actually processes can have maps of the system space also through this mechanism. That's how you share the library code. So address translation, page size is specified by the ISA. It used to be much smaller in the early days. In VAX it was 512 bytes. Today there are multiple page sizes. I think in x86 it's 4 kilobytes, the smallest page size. In Alpha it's 8 kilobytes, and x86 has 2 gigabyte pages as well. I always forget if it's 1 gigabyte or 2 gigabytes. 2, okay. I got it right.
You can also have 4 megabytes.
Oh, they also have 4 megabytes?
Yeah.
Oh, 4 megabytes, okay. Yeah, there's another granularity here. So page table contains an entry for each virtual page. This is called the page table entry, as I showed you there. So what's in a PTE? I kind of showed you, so I'll do that again. But let's end with this, and then we'll pick up here. So basically, a page table entry is an entry for the virtual page number, and its purpose is to do translation. Well, actually, it serves multiple purposes. First, it has a valid bit. Is the page present in physical memory? If not, then these things can store the address of the page in disk. If yes, let's assume that it's yes, then this page physical frame number tells the physical frame in main memory where the page is stored. You also have other bits. One is a dirty bit. Well, what's the purpose of that? Purpose is the same as the dirty bit or modified bit in a write-back cache. Because what's happening here is really, you have your disk, and you have your main memory, or DRAM, and your DRAM is really a cache for your disk. And your page table, if you will, is a tag store. Right? We have a sophisticated mechanism that's your tag store for your entire DRAM. And the dirty bit says the page that's currently in DRAM, somebody wrote to it. So it's not the same as the page that's stored in disk. So if you're going to replace this page in DRAM, you'd better write back the contents, otherwise you're going to lose them. So that's the purpose of the dirty bit. So this is no different from the cache we've seen, except it's managed in a slightly different way. It's managed by the operating system. We have other things. Well, I'll get to the protection bits, but we have a reference bit. This doesn't have to be there. But this bit tells whether the page has been referenced in the recent past. Now, why might you want to have something like this? Exactly. You may want to use that bit when you're running out of, when you get a page fault, right? When you get a page fault, you might want to, now you have a choice in your hand. Because it's a cache, you're going to evict a page that's in DRAM. Now what page do you evict? Well, you may want to pick a random one, right? We've seen all those policies for cache management. You could use any of those here also by adapting it to the requirements of the disk. But random. If you didn't have this reference bit, you could pick random. Now most OSs or hardware uses this reference bit. What is done is when a page is accessed, this reference bit is set. And periodically, the OS goes through the page table and clears these reference bits. So this reference bit tells you some of these pages, the page has been accessed after the last time the OS cleared these reference bits. So it tells you this page was recently used. Of course, you could imagine more sophisticated mechanisms, right? You could actually keep track of which, and allow you order across all the pages in your main memory. Now, this may be a bad idea, right? Because you have so many pages in your memory. So you run into the same issues that you run into caches, because this is essentially a cache. And this is your tag store. Well, we'll have some other bits, and I'll tell you about those other bits, because I think we've already run out of time. But next time, if you read, I'll put up the remaining slides on the website. If you do the reading and look at the slides, hopefully we'll finish virtual memory next time.